Open a fridge, and the answer feels obvious. Cold air spills out. Your milk is chilled. Your leftovers are safe. The ice tray is frozen solid. It all feels so ordinary that most of us never stop to ask one very strange question. How does a metal box sitting in a warm kitchen stay cold all day, every day? Because a fridge is not filled with some magical supply of coldness. It is surrounded by warmer air. People open the door, food goes in at room temperature, heat is constantly trying to sneak inside, and yet the inside stays cold enough to keep food safe. That is an extraordinary trick when you think about it. So what is really happening? How does a fridge fight heat all day without feeling dramatic? Why is the back of a refrigerator often warm? Why does it sometimes make a humming sound and then go quiet again? And what exactly are all those coils, compressors, and hidden parts doing? In this video, we are going to break that down in the simplest possible way. Because a fridge does not really make cold. It does something more interesting than that. It moves heat. And once you understand that idea, the whole machine starts to make sense. DOE explains this directly by comparing refrigerators to heat pumps in reverse. A refrigerator pulls heat from inside the box and sends it into the surrounding room. That is the first big idea. A fridge stays cold by taking heat out of the inside and dumping that heat somewhere else. In most homes, that somewhere else is simply the room around the fridge. That is why the outside parts of a refrigerator, especially near the coils or mechanical compartment, can feel warm. The machine is not creating cold air from nothing. It is carrying heat away from where you do not want it and releasing that heat where you care less about it. DOE's explanation of compressor coolers makes exactly this point. The refrigerant picks up heat, and the system later releases that heat into the surrounding air. Once you understand that, the next question is obvious. How does the fridge actually move heat? The answer is the refrigeration cycle. That sounds technical, but the basic idea is easier than it sounds. Inside a typical refrigerator, a special fluid called a refrigerant circulates through a loop. That refrigerant is useful because it can change state under the right conditions. It can absorb heat in one part of the system and give off heat in another. DOE describes compressor coolers in these terms. The refrigerant expands into a gas and absorbs heat. Then later pressure is applied, so it turns back into a liquid and releases the heat it was carrying. NIST likewise describes the cycle with a simple principle. When a gas is compressed, it heats up, and when it is later cooled and expanded, its temperature drops much lower. In a standard fridge, this cycle depends on four main parts. There is a compressor, which keeps the refrigerant moving and raises its pressure. There is a condenser, where heat is released to the room. There is an expansion device, where the pressure drops suddenly, and there is an evaporator, where heat is absorbed from inside the fridge. ASHRAE identifies those four pieces, compressor, condenser, evaporator, and expansion device, as the essential parts of the basic vapor compression refrigeration system. Now, let's turn that into a simple story. The refrigerant leaves the inside cooling part of the system as a low-pressure vapor and enters the compressor. The compressor squeezes it. That raises both its pressure and its temperature. In other words, the refrigerant gets hot. From there, the hot, high-pressure refrigerant moves to the condenser. This is the part of the system where the fridge dumps heat into the room. As the refrigerant gives off heat, it cools down and condenses back into a liquid. ASHRAE describes the condenser as the heat exchanger that rejects the heat absorbed by the evaporator along with the extra heat added by the compressor's work. After that, the liquid refrigerant passes through the expansion device. This is a small restriction in the system, but it has a big effect. The refrigerant suddenly drops in pressure, and that pressure drop makes it much colder. Now the refrigerant is ready for the evaporator, which is the part that actually cools the inside of the fridge. Here, the cold refrigerant absorbs heat from the refrigerator compartment. As it absorbs that heat, it evaporates back into a gas. Then the cycle begins again. That loop is the heart of the machine. Heat is picked up inside the fridge, carried through the refrigerant loop, and then released into the kitchen. NIST's refrigeration cycle diagrams and DOE's consumer explanations both support this basic sequence. This also explains one of the most surprising things about refrigerators. A fridge can make your kitchen slightly warmer. That sounds wrong at first, but it is exactly what should happen. The refrigerator removes heat from the inside compartment and dumps it into the room. On top of that, the compressor itself uses electricity, and that energy also ends up as heat. So a refrigerator is not a cold generator in the room as a whole. It is a heat-moving machine. DOE's heat pump explanation points to the same logic. Refrigerators remove heat from one place and reject it to another. Now, a fridge obviously does not run at maximum effort every second. That is where the thermostat comes in. The thermostat monitors the internal temperature and decides when the cooling cycle needs to run. When the inside gets too warm, the system turns on. When the temperature is low enough again, the compressor cycles off. DOE's explanation of compressor coolers notes that when attached to a thermostat, compressors cycle on and off to keep temperatures within the desired range. That is why your fridge sometimes hums and sometimes goes quiet. The machine is not confused. It is responding to temperature changes. When you open the door, warm room air enters. When you place warm food inside, extra heat enters. When the kitchen itself gets hotter, more heat tries to leak through the walls of the fridge. The thermostat senses the result, and the system responds. That brings us to another hidden part of the story: the fridge's walls and door. A refrigerator only works well if it slows down the heat trying to get in. That is why insulation matters so much. The cold air inside is useful only if the outside heat cannot rush in too quickly. Older refrigerators also used foam insulation that created environmental concerns, and EPA notes that household refrigerated appliances historically used refrigerants and foam systems that required careful handling and disposal. The door seal matters for the same reason. If the seal around the door is weak, warm air can leak in continuously. Then, the fridge has to run harder and more often to remove that extra heat. The machine can still work, but it becomes less efficient and may struggle to hold temperature as well. So a fridge is not just the compressor and coils. It is also a well-insulated box designed to make the heat removal job easier. This is also why people are told not to leave the fridge door open too long. The moment the door opens, cold, dense air spills out and warmer room air comes in. Then the fridge has to remove that added heat all over again. DOE's refrigerator temperature guidance also makes clear that proper cooling matters for food safety, with the main refrigerator section ideally around 35 to 38 degrees Fahrenheit and always under 40 degrees Fahrenheit. Some refrigerators add another layer of convenience with frost-free systems and internal fans. The exact design varies, but many fridge-freezer combinations use fans to move cold air where it is needed and automatic defrost systems to stop frost from building up excessively on cooling surfaces. That way, the inside keeps feeling simple and low maintenance, even though the machine is managing temperature, airflow, and frost in the background. And that is really the bigger theme here. A fridge feels boring only because it is doing its job so well. Inside that quiet kitchen appliance is a repeating thermodynamic loop, a pressure system, a control system, an insulated enclosure, and a heat transfer process that runs so reliably that most people stop noticing it entirely. Even the refrigerants themselves are part of a larger infrastructure story. EPA notes that many older refrigerants were ozone-depleting substances, and later substitutes such as HFCs, while safer for the ozone layer, can still have significant climate impacts. That is one reason refrigerant handling and disposal are regulated, and why fridge technology has changed over time. So the next time you open your fridge, it is worth pausing for just a second. That cold air is not sitting there passively. The appliance has been working to remove heat, move it through a refrigerant loop, push it out into the room, and keep the temperature inside stable enough to protect your food. It is not making cold. It is moving heat with just enough speed and consistency that the inside of the box feels like its own little climate. That is how fridges stay cold. And like so many hidden systems, the better they work, the easier it is to forget how impressive they really are. If you enjoyed this video, make sure to like and subscribe to Hidden Infrastructure of the World. Also, comment down below what hidden infrastructure you want to see next. See you in the next video.